Welcome to the Foundry by Ford's College. So, in our last session, we wrapped up planning reusable deployment scripts, mapping out exactly how we get our code onto the blockchain. But now we're rolling up our sleeves to draft the actual internal blueprint for our secure smart contracts. In this explainer, we're going to take all those abstract access control ideas you've been learning and literally forge them into a tangible, working Solidity implementation. We're essentially building the machinery that dictates exactly who is allowed to do what inside your protocol. Let's get into it.
Okay, let's dive into this. Here is the master schematic we're assembling today. We'll be covering designing the blueprint, storage layout and mechanics, the grant and revoke workflows, building the onlyRole gatekeeper, real-world access scenarios, and finally, wrapping up the machine. All right, let's start with phase 1 of our engineering schematic, designing the blueprint. This is where we define the unique mechanical parts that will actually identify our roles. So to identify roles, we use a specific data type called bytes32. Now, you're probably wondering, why not just use a normal text string like minter? Well, here's the deal. In the Ethereum virtual machine, strings are dynamically sized, meaning they can be pretty massive gas guzzlers. A bytes32 identifier, on the other hand, is a fixed, compact 32-byte hash. It's usually generated using the CAC256 function. Think of it less like a sprawling, handwritten paper label and more like a highly efficient, standardized serial number stamped right into metal. It gives us that human readability we want in our source code, like modifier, while keeping things incredibly gas-efficient and lightweight for the machine runtime. Moving on to Section 2, Storage Layout and Mechanics. Now, what's really interesting about this is how we actually file these roles away securely inside the contract's storage. To keep track of who holds which role, we use a nested mapping. The syntax looks a little something like this. Mapping bytes32, mapping addresses to bool. Imagine this as a super organized physical spreadsheet, or maybe a really exclusive digital guest list. That first column, that's the role's bytes32 identifier. The second column is the specific Ethereum account address, and that final column is just a simple Boolean checkbox, true or false. Because it's a mapping, the contract doesn't have to scan through some giant list of names. It acts as an instant, mechanical O of 1 lookup. You basically ask the contract, hey, does this specific address hold this specific role? And it instantly checks the box and says true or false. There's absolutely no waiting in line while the bouncer checks a clipboard. You either have the VIP stamp or you don't. Obviously, a static guest list isn't going to cut it. We need a way to dynamically flip those Boolean switches. So let's look at Section 3, the grant and revoke workflows. To flip those switches in our storage mapping, we build two mutating functions, which are strictly controlled by an administrative role. GrantRole and revokeRole are the exact inverse of each other. Just picture them as physical on and off toggle switches. But here's the kicker. They don't just change the state to true or false. They also emit events, role granted and role revoked. Emitting an event is basically the smart contract printing a permanent auditable receipt log right on the blockchain. This is absolutely crucial because it allows off-chain tooling, dashboards, and automated testing suites to see exactly who got power and who had it taken away, without having to manually dig through the contract's entire storage history. Section 4. Building the onlyRole gatekeeper. Let's move to this next part and see how we actually build the defense mechanism for our contract. This is where the magic really happens. We wrap our sensitive functions with a custom modifier called onlyRole. Picture this modifier as an automated toll booth or a really strict bouncer standing right in front of your protocol's machinery. When an external call tries to trigger a protected function, step 1, boom, they hit the toll booth. Step 2, the onlyRole modifier intercepts that call and interrogates the user by triggering a helper function called hasRole. It checks that nested mapping we just talked about to see if msg.sender, the person actually making the call, possesses the required role. Step 3, if the mapping reads true, the gates swing open and the code executes. If it reads false, the transaction instantly reverts. No entry. And when that transaction reverts, we definitely don't want it to fail silently. So we program our onlyRole modifier's require statement to spit out this exact message. AccessControl account lacks role. Honestly, you can think of this as a giant denied stamp just slamming down on the forehead of an unapproved MSG sender. Okay, it might seem a bit blunt, but trust me, this specific descriptive revert message is going to be your absolute best friend. It literally saves you countless hours when debugging, and it lets your automated test assertions actually verify that your security toll booth is rejecting intruders for the right reasons. Section 5. Real-world access scenarios. Now that our machinery is fully assembled, let's look at how it operates out in the wild. And this brilliantly illustrates why understanding this pattern is so foundational to Web3. I mean, we see this access control schematic everywhere. In token minting systems, a deployer might grant the minter role to a specific trusted smart contract, just so random users can't start printing free tokens. We use it for initializing protocol configurations or managing governance through multi-sig wallets. In fact, across the wider learning programs we do at Forge College, we talk a lot about the lifecycle management pattern. This is where a team grants admin powers to a secure multi-sig during launch, but then later uses that revoke workflow to permanently lock the configuration, making the protocol truly be centralized and trustless.
Finally, Section 6, wrapping up the machine. Let's tie all these components together.
So the absolutely crucial takeaway here is that by implementing this minimal access control pattern, you're building a highly robust, composable security module. Let's recap. We used compact bytes 32 identifiers to save on gas. We built a nested mapping so our permission lookups are instantaneous. We established crystal clear workflows with auditable event receipts. And lastly, we locked the whole shebang down with a gatekeeper modifier. There's a reason this blueprint is the industry standard. It's clean, it's testable, and it is incredibly secure. But before we wrap up this explainer, I'm going to leave you with a bit of a provocative warning to ponder. What happens to your protocol if you accidentally revoke your own default_admin role before you've assigned a new one? Well, the short answer, you just locked yourself out of your own machine. Forever. Yep, there is absolutely no customer support hotline on the blockchain to reset your password. It is a permanent, irreversible operational failure. And honestly, that is exactly why automating and testing these configurations is so incredibly vital. To dive deeper into how to automate these flows safely and to jump into our next lesson on scripting, make sure you head over to forge.college. Check out our comprehensive programs and join the community to really master these Web3 architectures. I've been your host for this explainer. Thanks for hanging out, and I'll catch you in the next one.